Hello all and welcome to this series of videos where we look at exponential functions and logarithms and how to solve exponential equations and logarithm equations. As you can see there, it's going to take us about 3 weeks, and this is chapter 13 from the textbook. These will be the recommended questions for the exercises. Pause if you do want to copy those down at all. But let's get straight into it. Today we're going to be looking at exercise 13A and 13B because both of these are technically revision of Year 9 curriculum, actually. So hopefully you remember them, and maybe you did some of them last year as well. But let's get straight into it. So here are the 6 index laws, the zero power law and the negative indices law, and also the rational law. So these are called 1, 2, 3, 4, 5, 6, the 1 through 6 index laws. This is called the zero power law. This is called the negative indices law, and then this is the rational indices. Down the left is the actual rule, and then on the right is some examples of them. Hopefully these are a bit of looking a little familiar. If not, the key things that catch people out is when we have the you need to pay careful attention to the base, so when the base is the same and when the base is different. So these rules, especially, I've put those numbers in completely wrong. That's 1, 2, 3, 4, 5. Sometimes the zero power one's called the 6 law. Either this one or this one, sometimes called the 6. But for 1 and 2, these rules only apply if they have the same base. So that's what the A and the A means. It has to have the same base. The powers can be different, and if we're multiplying these two terms together, we can add the powers. The exact same situation if the bases are the same, but we're dividing, or it's written here as a fraction as well with the same base, then we subtract the powers. If we have something to the power of m and then that whole thing is then also have a power, we can multiply the powers. If we have a power outside, something that is made up of multiple things multiplied together, we can actually bring that power into each of the individual items. This only works, this fourth law only works when the items are multiplied together. Sorry, this fourth law only works if they're multiplied together, so it doesn't work for addition. And then the fifth law is sort of another version of the fourth law, where if we have two items that are divided, and then that's all to the power of n, we can bring that power into both of them as well. You can't apply law 4 and law 5 if there is a subtraction. So if you had a minus b to the power of 5, or even to the power of 2, as we know, we can't just turn that into a squared minus b squared. That's not correct, and we would know that if we just did the binomial expansion of that. So law 4, law 5 only work if everything's either multiplied or divided. Zero power says that anything to the power of 0 is 1. Negative index law says if we have something to the negative power, instead we can effectively, we can just bring it to the bottom of the fraction, or we can put it in the denominator, and then it turns the power positive. It switches the sign. We also have the version of it that if we have 1 on a to the negative m, we can, same thing, if we bring that to the opposite side of the fraction, in this case we could bring it up since it's a negative power, this now turns into a positive power. But yeah, pretty much that's saying if you have a negative power, put it in the opposite side of the fraction and you can change the sign of the power. And then the rational indices is exercise 13b, which we'll get to in a minute. So we've got a couple problems here that I'm just going to go through really quickly, not so much explain, just give you the full working out. Look at a prime decomposition, then there's a whole bunch of practice problems left for you to try in your own time. So let's get straight going into it. 3 to the power of 4 times 3 to the power of 2. We have the same base, so that's going to be equal to 3 to the 4 plus 2, which is equal to 3 to the power of 6. B, we want to look at things that have the same base, so we're going to look at the A bases, we're going to look at the B base, and then we're going to look at the C base and combine those, because this could technically be written as A squared times by A times by B times by B to the 4 times by C cubed times by C to the power of 5, because commutative law says that order of multiplication doesn't matter effectively. So we get A squared times by A, which is effectively A to the power of 1, so that becomes A to the power of 3. B times B to the power of 4, again B is technically B to the power of 1, so that becomes times by B to the 5. And then C cubed times by C to the power of 5 is 3 plus 5 is 8. So without the multiplication signs in there, we can just write it A to the power of B, B to the power of 5, C to the power of 8. Okay, same thing here in question C. We have the same base, so we can do the A2 plus, and I'll just put in brackets what the second power is, just to avoid any sign issues. But that just 2 plus 2b plus 2, so that just turns into A to the power of 4 plus 2b. Yeah, so that's just using index law 1, all of those problems. These ones here, we are using index law 2, and same thing, we just want to look at the items with the same base. So we have A and A, we have B and B. Again, A by itself is technically A to the power of 1, B by itself is technically B to the power of 1. So A squared divided by A, we'll get A to take away 1. Then we have the B cubed divided by B to the power of 1, so we get B3 take away 1 is equal to A B squared, or A to the power of 1 B squared, but we don't need to write the power of 1. Okay, one thing to note here is that we don't always get where this simplifies that stuff on the top, so we might in this case have A squared B squared on A B to the power of 4. So in that case, the bigger power here is on the bottom, so we're going to get A2 take away 1, and then we're also going to get B2 take away 4, which is equal to A to the 1, B to the negative 2, which if we go back to using negative indices law, we know that we can also actually now write this as A to the power of 1, move the B down to the bottom of the denominator, bottom in a fraction, and that means we can write it with a positive power, which sort of makes sense. We had 2 at the top, 4 at the bottom. Take the 2 from the 4, we're left with 2 at the bottom. So there's an example where you're not always going to end up with everything up top, nice and simple. Example E, we have A to the 3x times by A to the 2x minus 1 on A to the 4x. So this is sort of a combo one. We have a multiplication at the top, and then we have the whole thing divided. So we can sort of work this using BidMass. We can do the multiplication and divide first, but we've sort of got this top bit, so we can apply index law 1 first. So we get A to the 3x plus the 2x minus 1, because those two are multiplied together, and then since the A to the power of 4x has the same base, we can then also take away the 4x from it. So we're going to get A to the power of 3x take away 3x plus 2x take away 4x, so that's going to be 5x take 4, so that is x, and then let's subtract 1, and there's our answer. The other way that some people might like to do this is just leave the A to the 4x on the bottom for now, simplify the top, so the top becomes A to the 3x plus the 2x minus 1, so we're going to get A to the 5x minus 1, and then apply the second index law, which says A to the 5x minus 1 take away 4x, so we get A to the x take away 1, which is the same answer. So when we start to get into the more complex index problems where you're trying to solve them and there's lots of terms, there's normally a lot of ways to approach them. You might be able to apply law 1 first, or law 2, or whichever the laws you're doing, but you should always get at the same answer. Rightio, here we got the negative index law, so 3 to the negative 2, that's just as simple as putting it 1 on 3, and to the power of 2, the power turns positive. 2 over 5 all to the power of negative 3, so same thing, I can write that as 1 on that whole thing, now with a positive power, and then using index law, which number is that? Number 5. We've got something that looks like just this. We can actually bring the power inside the brackets. So this is now 1 on 2 to the 3 divided by 5 to the 3. And simplifying, we have 1 divided by a fraction. How can we divide by a fraction? Well, that's the same as 1 times by the fraction flipped. So we now get 5 to the power of 3 on 2 to the power of 3 is our final answer. Right. Example H, there's a lot involved in this. We have a couple things. We have a b to the power of 0. So anytime you see something to the power of 0, instantly just turn that into 1. That's going to make your life a lot easier. B to the 0, so that just becomes times by 1, so I don't even need to write it. To the power of 2 times by 4a to the 5c to the negative 2. And again, there's a whole bunch of different ways we could bring this in first. We can bring this in, or since it's negative, we can actually bring this whole term down the bottom of a fraction to make it a positive power. So let's actually do that. So we get 3a all squared to the 2 divided by 4a to the 5c to the power of positive 2, since we brought it down the bottom. Now we're going to just bring those squares inside. So we get 3 squared a to the power of 4, because we bring it inside to everything. And same here, we have to bring this 2 inside to everything. So we get 4 squared a to the 10c to the 2. And now we can do some simplifying. So 3 squared a to the 4 over a to the 10. If I just put this over here at the side, that's the same as a to the 4 take 10, which is a to the negative 6, which is 1 on a to the 6. So I'm left with 4 squared a to the 6 on the bottom, c squared. And there's our answer. Rightio, prime decomposition. All of these problems were all nice and easy where everything had the same base. Sometimes it's not going to be so nice where we have, and we can only do this when it's numbers as the base, but when we have numbers as the base, we need to do what's called prime decomposition, which any number as the base, we need to convert it into a product of primes. So 24 is actually the same as 2 times 2 times 2 times by 3, which can be written as 2 cubed times by 3. Which is what's put in there. It is a product of all prime numbers. 2s and 3s are prime. 24 is not prime. 6 is not prime. 4 is not prime. So you need to write it as a bunch of prime numbers multiplied together. You can do that for every single number that exists. Every single integer number, I should say. Turns out you can do a prime decomposition of it. Same with 18. 18 is the same as 3 times 2, which we just write as 3 squared times 2. Once you've got a prime decompositions, you can bring the powers in, which is what's happened here. Bring the power in, and now we have some things with the base 2, which we can combine, and some things with the base 3, which we can combine, which goes from there. So let's have a go at that. So simplify the following expression. Simplify the following, expressing your solution in the form of a over b to the power of x. So we need to get it where we have two numbers, and it's just those two numbers to the power of x. So we have 8, 6, 16, none of them are prime, same with 4 and 36. So 8 is the same as 2 cubed, so we get 2 cubed to the power of 2x times by 6 is 2 times 3 to the power of x times by 16 is 8 times, that's 2 to the power of 4, the negative 2x, all divided by 2 squared to the x times by 36. What's that going to be? That's the same as 6 times 6. 6 is the 3 times 2 times 3 times 2. So that's going to be 3 squared times by 2 squared, all to the power of negative x. Let's come up here and start simplifying. So we get 2 to the power of 6x times by 2 to the power of x times by 3 to the power of x times by 2 to the negative 8x, all divided by 2 to the power of 2x times by 3 to the power of negative 2x times by 2 to the power of negative 2x. Okay. let's simplify now. We'll simplify the numerator. We have 3 things with base 2. So all those powers can get added together. So we get 2 to the 6x plus x minus 8x times by 3 to the x, all divided by 2 to the 2x times by 2 to the 2x. So I'll just put it over here so you understand we're effectively doing that, which is equal to 2 to the 0, which equals 1. So we just get 1 times by 3 to the negative 2x, and the 1 we can just disappear. So we get 2 to the power of 6x plus x is 7x, take away x, so negative x times by 3 to the x on 3 to the negative 2x. That gives us, let's bring this down the bottom and this up the top to get rid of the negative powers. So we get 3 to the x times by 3 to the 2x divided by 2 to the x. We finally get 3 to the 3x on 2 to the power of x, which we can write as equals to 3 to the 3x. That is the same as, again, just because I'm running out of space, I apologize down this bottom right here. 3 to the 3x is the same as 3 to the power of 3 power of x, which 3 to the power of 3 is 3 times 3 is 9 times 3 is 27 to the power of x. So we finally get 27 to the x on 2 to the x. Let me just write it up here a bit bigger. On 2 to the x, which, since it's the same power, we can bring that outside as 27 on 2 to the power of x as required. So there's a lot involved in that problem, and a lot of the index laws, pretty much all the index laws come into it. What are we at? 17 minutes. There's a bunch of practice problems for you to do. Pause to see that screen. There's some more practice problems. This one is certainly got a lot going on in it, but is also definitely achievable. And finally, what have we got? 2.5 minutes left. We can look very quickly at the rational index law, or how we can, if we have rational indices. So rational means just when we have a fraction, and it starts from, if we have a to the 1 on something, we can write it as that y root. So for example, a to the half is the same as the square root of a to the third is equal to the third root of a to the power of 1 on 15 is equal to the 15th root of a. And then we can take that a step further, as if the numerator is not 1, say if we have some other number, we can break that down using the index laws into a to the 1 on y with the b outside, and then we can then write in either of these two forms. So realistically, you want to be able to go from that straight over to this, or straight over to this. Whatever's on the bottom is what the root becomes, whatever's on the top can go all the way outside or come inside as the power. So let's have a go. 25 to the half, well, that's the same as the second square root of 25, which the square root of 25 happens to be 5. 8 to the 4 on 3, that is equal to the, since the 3 is the bottom number, we're going to get the third root of 8 all to the power of 4. And I suggest putting this power 4 outside. And I'll show you why, because it turns out the third root of 8 is 2. 2 by 2 by 2 is 8. So by leaving this outside, a lot of the time you'll actually be able to simplify this. So we actually now get 2 to the power of 4, which 2 to the power of 4 is 16. You could have done 3 to the 8 to the power of 4 and then figured out what 8 to the power of 4 is, but you'd have to do a lot of scribbling on your paper. What is 8 to the power of 4? 8 to the power of 4 is 4096. And I don't know how many of you know off the top of your head that the cubed root of 4096 is 16. So that's why doing it this way with the power outside is generally allows for an easier simplification. Rightio, example C and D. I've gone a little bit over the 20 minutes, I apologise, but these are the last two examples. So we now get, let's bring this in to everything. So we get a to the -2 on 2. I'm just bringing in the power of half to everything. C to the half times by a squared b squared on c to the -4. Which I can now write as a -2 divided by 2 is just -1, b to the half, c to the half, times by a to the 2, times by b to the 2, all divided by c to the -4. So what do I get? Simplifying, so collecting some like terms. I'm going to get the a, and the a is just becomes a to the 1. The b becomes half plus 2. That becomes 2.5, which is 5 on 2. And then the c, we have the half up top and the -4 on the bottom. That's going to become that would actually be c to the half, take away the -4 because we're dividing by the negative. So that's going to be a b to the 5 on 2. Take away that's going to be 4.5. So that's c to, what's 4.5? 2. That's 9. Yes. There we go. Now we can finally apply the rational index law. Both of these have 2 in the bottom, so we get a square root of b to the 5. I might just put the 5 inside this time. And same square root c to the 9. Rightio. Whew. Bit in that. Again, many different ways you could have gone about simplifying that, but that's where you should have gotten as the answer. Now, this last one is really nice. This 2x plus 3 is all inside the square root, so we can write the 2x plus 3 all to the half. And you might be thinking, what do I do from here? What you need to notice is that both of these are exactly the same. So I've technically got 2x plus 3 to the 1, and then 2x plus 3 to the half, and then multiply together. So we could think of that whole thing as a to the 1, and then a to the half. So when it looks like that, it's a whole lot simpler, and you're like, oh, I just need to add those powers, and I'm going to get a to the 3 on 2. But instead of it just being the a, you need to recognize that that whole bracket is the base. So we can now write this as 2x plus 3 to the 1 plus half, which is equal to 2x plus 3 to the 3 on 2. Which we could write that as, probably would write it this way, 2x plus 3. We're taking the square root of it, and then all of that is to the power of 3. The other way you could write it, of course, is like that. Both of those would be the same answer. And that's it. So that's a really quick refresher on the index laws and rational indices. I highly suggest that you go back and do these practice problems, and then, depending on that, use it to guide which questions you do from exercise 13A and 13B. If you really struggled, well, then you need more practice. Go do more practice. If you really crush those practice problems, well, then still go back and do a couple of the textbook questions in class. As always, if you have any questions, feel free to comment below, put something on Google Classroom, shoot me an email, or ask in class. I hope you have a good evening.